Hello. In this video sequence, I'm going to derive a conservation equation for flow and transport in a porous medium. I'm only going to consider Darcy flow, that's essentially going with the flow, plus molecular diffusion. So I'm going to combine those two, plus conservation of mass, to come up with a partial differential equation in one dimension for how something dissolved in the water might move. Now, the way in which I'm going to approach this problem is as follows. I'm actually going to start with a blank sheet. Now, normally these conservation equations are equation one in a textbook. You sort of memorize them and then forget them and maybe do some analytic solutions. But in fact, I'm going to take care of the derivation. Derivation isn't terribly complex, but it's important that you understand the steps so that you can derive your own conservation equations if you want to include more physics or we want to do something a little bit more complex. So, as I said, we've got a blank sheet here. What I'm now going to consider is flow from left to right. That's what that red arrow is, right? We got some flow from left to right. We have something dissolved, say, in water that's flowing through a porous medium. And what we're going to do, as I said, is we're going to consider conservation of mass. So how we go about that is we consider a little box. Okay, drawn here. Okay, so there's a box. And what do I mean by this box? Well, what I mean by this box is that we have a box here that I put at a location X. Okay, and then we're going to consider a small box. So here is a location X plus delta X, and I'm obviously going to allow delta X to tend to 0 at a judicious moment. And we have some cross-sectional area A. And what we now have is we have some flow into the box, which I'm going to give a symbol F for flow or flux, and that's at a location X. And I'm going to have some flow out of the box, and that's going to be at a location X plus delta X. Okay, so that's what we're going to consider. And now you may be saying, okay, but what is my F? So F here is equal to UC minus phi d dc dx. Okay, so let's that isn't an F prime there, so let's make that a bit clearer. This is F. Okay, so what are those two terms? The first term here, Q, is the Darcy velocity. So this represents the volume of fluid flowing per unit area, per unit time. It's multiplied by the concentration. In this particular example, and it's not vital that we do this, but in this particular example, I'm going to assume that the concentration is a mass per unit volume. So then the units of F are in fact a mass per unit area per unit time. Okay? This second term here, phi d m dc dx, is from Fick's law of diffusion applied to a porous medium. I is the porosity, d is the molecular diffusion coefficient, dc dx is the concentration gradient. And for those of you who see my previous video of this is where this was first presented. So this is my flux. Now what I've said is I want to impose conservation of mass. Now conservation of mass is quite simple, so let's just write it down. Mass in minus mass out, okay, is equal to the change in mass. Right? So now what we need to do is we need to talk about what that means. So we've got something dissolved in the water, it's flowing into the box, and some of it's flowing out. And of course, there's some massive solute in this box shown in red. Okay? So we're going to consider a small time delta t, and we're going to say, well, within that small time delta t, how much went into the box, how much went out, and that must be equal to the change in mass. So let's write over here, okay, what the mass in the box is. Well, we've got a porosity phi. Let's start with it being a porous medium, we know that. It has a cross-sectional area A and a length delta X. So that's the volume, essentially, of water or fluid within the box. To make it into a mass, we need to multiply by something that has mass per unit volume. That's not a density, strictly speaking, it's a concentration C. It's the mass of solute per unit volume of the fluid. Okay, so phi L delta X C is the mass in the box. So the change in mass clearly is phi A delta X, that volume doesn't change, okay, times the change is, well, how much concentration do we have at the end? So that's at a time t plus delta t. And how much did we have at the beginning, which is the concentration at a time t. Okay, simple as that. So that's the change in mass. That's got to be equal to the mass in minus the mass out. Now the flux F, well, it's obviously related to F, isn't it? But the flux F I've defined, and you've got to be really careful on the definitions, okay? Don't get sort of get loose or vague about it or confused. F has the units of a mass per unit area per unit time. So I've got to multiply it by an area, right? And I've got to multiply it by time to get a mass, okay? And then the mass in is my F evaluated at location X minus the mass out, the flux out, which is evaluated at location X plus delta X. Okay, so that, in the end, is all I need to do to invoke conservation of mass. Now, what am I going to do now? I've got this equation, okay, then what I'm going to do is I'm going to cancel out the areas, okay, A cancels. And then what I'm going to do is I'm going to move all of this term, okay, over to this side of the equation, okay. Then I notice I've got a delta X here. I'm going to put that down here, so it's going to be over delta X. And there's a delta T here, and I'm going to put that down, okay. So let's see what that arrives at. Don't panic about this. Just take your time looking at it, okay. What am I going to get? Okay, if I try and okay, so this is the porosity. Okay, I've got this C term. Okay, so let's do that. I've got my C, okay, of T plus delta T minus C of T. Okay, and that's all got divided now by delta T. Okay, now this term I move to the other side, so the signs are going to flip. So now this is F of X plus delta X minus F of X, and that's all divided by delta X, and that is now equal to 0. And I'm going to take the limit, right, of delta T and delta X go to 0. So it should be quite straightforward. C of T plus delta T minus C of T divided by delta T, and the limit that delta T goes to 0 is dc dt, and this is df dx. Okay, so hopefully that's straightforward. So over here, I can actually write the equation. Okay, so it's phi dc by dt, okay, plus df by dx equals 0. Now, you might be saying, well, why are these curly Ds? Is that my bad writing? No, that's a partial derivative because the concentration will depend not just on time, but also on distance, similarly with F. I use a partial derivative because this is a time derivative in the box. Okay, so we have things happening in the box. There's a time derivative, but for F, it's a spatial derivative. Now, what I'm going to do is I'm going to insert the F that's written at the top here into the equation. Q, the Darcy velocity, the volume per unit area per unit time. I have an incompressible fluid is actually fixed for one-dimensional flow. So imagine you inject a cubic centimetre of water, for instance, into a rock. A cubic centimetre has to come out, assuming that the water itself is not compressing. So if you have incompressible fluids, and in fact, at the small scale, that's certainly a very good approximation, we have incompressible fluids, then Q is a constant. And so the equation becomes phi dc by dt, right, that's fine, plus Q comes out of the derivative, I've got a dc by dx. Then we got a minus term, but I put it over the other side of the equation, right? I assume that phi and dm are also fixed in space, and then I get this equation here, okay? And this is called the ADE, the advection diffusion equation, traditionally. So the ADE in one dimension has this form, phi dc dt, so phi times the change in concentration, plus q dc dx, so the spatial derivative. And then on the right-hand side is this diffusion term, the second order term due to diffusion. Now, this is a derivation in one dimension. It's very straightforward. It's just looking in a box. You can extend this if you're interested to 3 dimensions. The 3-dimensional extension essentially changes this term here. You end up with a q dot grad c term, and here is a Laplacian del squared c. It's quite straightforward if you consider a box with flow in all 3 dimensions. But I'm not going to dwell on that here. I'm just going to look at the one-dimensional form of that for today. So that actually ends what I wanted to talk about there. It's derivation of the advection diffusion equation in one dimension, relatively straightforward. But the key thing here is not worrying about the equation. Equation is important, we don't want to get it wrong, but how we derive it. Relatively straightforward. Keep calm. Just think of what's going into a box, what's coming out, and the change. It's exactly the same with lots and lots of different applications. But this is the first one, relatively straightforward one. So at that point, I'll end here. Thank you.